inhale and the volume in the lungs goes up. You inhale about a half liter with each quiet breath, and then you begin to exhale and the volume goes back down to the FRC. This should be very easy to understand. Volume is just going up and down during a respiratory cycle. In the middle of the graph is the change in alveolar pressure during a quiet breathing cycle. So remember, we always begin at atmospheric pressure of 0. That's where we start a quiet breathing cycle. The pressure in the alveoli becomes negative, and that draws air into the lungs, and then the pressure begins to rise and goes back up to 0. It's at 0 at the beginning of inhalation and at the end of inhalation. Then we begin to exhale. The pressure in the alveoli becomes positive. This pushes air out of the lungs, and then we come back to 0 once again. So in terms of alveolar pressure, we begin at 0. We're at 0 in the middle of a cycle, and we're at 0 at the end of a cycle. During inhalation, the pressure becomes negative, and during exhalation, it becomes positive. And then finally, at the bottom is the intrapleural pressure, and this is the one that's often tricky to understand, so make sure you get this. The intrapleural pressure is always negative. It begins at about -5. At the end of inhalation, it's down to about -8, and then it goes back up to -5. So the pressure in the pleural space is always negative during quiet breathing, whereas the pressure in the alveoli is fluctuating from 0 to negative to 0 to positive. Once again, make sure you understand this graph on the screen. This is the basis for lots and lots of Step 1 questions. So up to this point in this video, we've talked about lung volumes and we've talked about lung pressures. And what we're going to do now is talk about volumes and pressures together because the two are related. When the volume of air in the lungs changes, so does the pressure and vice versa. So years ago, physiologists began studying lungs, and they did this by removing the lungs from the body, either of cadavers or animals. And what they did was they applied pressure to the lungs and they watched how the volume changes. And they found a relationship like what is shown in this slide. When there is no pressure inside the airways, the lungs have no volume. They're completely collapsed, just like a balloon with no air inside of it. As you begin to apply pressure to the walls of the lungs begin to expand, and the y-axis here is volume. And so you see that the volume goes up until it reaches some maximal value. This is a fairly straightforward relationship to understand, and it's what happens if you apply pressure to the walls of the lungs outside the body. Then physiologists began to study the pressure-volume relationship of the lungs inside the chest cavity when they're being used by a living human being. And they found the relationship shown on the slide here. And as you can see, it's very different from the relationship we saw on the last slide for the lungs outside the body. So for a long time, people struggled to explain why the pressure-volume relationship of the lungs is different when the lungs are outside the body compared to when they're inside the body. Notice that when the lungs are inside the body, even when there's no pressure in the airways, there is still a volume. In other words, the lungs never completely collapse the way they do when there's no airway pressure outside the body. Also notice in the green line that as you apply more pressure, you do add volume to the lungs, but not as much as if the lungs were outside the body. You can also apply a negative pressure and begin to shrink the lungs. So people tried to understand this for a long time, and eventually they figured it out. The reason that the lungs behave differently in terms of the relationship between pressure and volume inside the body is because the lungs are not there all by themselves. The lungs are also affected by the chest wall, and the chest wall has its own pressure-volume relationship, and that affects the volume of the lungs. When the lungs are by themselves, there's nothing outside of them that modifies their volume, but when the lungs are in the body, the chest wall is outside, applying that negative suction pressure we talked about before, and that influences the volume of air in the lungs. So let's look at the chest wall volume pressure relationship all by itself. Like I told you before, if this is a wall of your chest, and your lungs are here in the middle, the chest wall wants to spring outward, and so that creates a negative suction type pressure in here that tends to open up the lungs and increase the volume. So if 0 pressure were applied to the walls of the chest, there would still be some volume here because they naturally want to spring outward. And you can apply positive pressure and increase that volume. You can apply negative pressure and decrease that volume. But the key point is that at a pressure of 0 on the chest walls, they still have a volume, and that's very different from the lungs. The lungs by themselves at a pressure of 0 have no volume. So now let's look at the three curves together. The blue curve is the lungs, the red is the chest wall, and the green is for the respiratory system as a whole. And what you can see is when there's no pressure inside the airways, the respiratory system as a whole is going to have a volume right here on the y-axis, and that volume is the FRC that we talked about earlier. What's happening at this point is at this volume, the tendency of the chest wall to expand the lungs, in other words, to apply negative suction and make the lung volume bigger, is perfectly balanced by the tendency of the lungs to collapse and want to have no volume inside of them. So those pressures between the lungs and the chest wall are balanced right here at the FRC, and that's why at the end of a quiet breath, you settle at that point where everything is in equilibrium. So let's review the concept of the functional residual capacity once again. We talked about this earlier. When this volume of air is in the lungs, the tendency of the lungs to collapse inward is balanced perfectly by the tendency of the chest to spring outwards. This is the volume of the lungs where they come to rest after quiet exhalation. And at this point, the pressure inside the system will be zero. There's no increase or decrease in pressure from push-pull of the lungs or the chest wall, and the pressure inside the lungs is zero, which, as we talked about before, is atmospheric pressure. Lung compliance is the change in volume you get for a given change in pressure. I've shown this equation here. And we talk about compliance in lots of areas of human physiology. We talk about compliance of the left ventricle of the heart, compliance of blood vessels, and we're talking about the same thing here. This is a measurement of how stiff the lungs are. It says if you apply a given pressure change, how much does the volume change? If the lungs are very compliant, it takes a small amount of diaphragm effort to generate just a small amount of pressure and you'll get a large volume change. So compliant lungs have an easy time moving air in and out because they easily expand and contract. Non-compliant lungs are stiff. You need to apply a large amount of effort from the diaphragm and a big pressure change just to get a small volume change because the lungs are stiff. And in non-compliant lungs, it's hard to move air in and out. And there are many disease processes where the compliance in the lungs changes, either where they become more compliant or less compliant. And this is related to the relationship between volume and pressure that we've been talking about on the last few slides. So let's talk about how changes in lung compliance change the shape of the pressure-volume relationship of the lung. Here's that blue line for a normal lung and the pressure-volume relationship when it's outside of the body. If the lung becomes non-compliant, in other words, if it becomes stiffer and has a decreased compliance, it will begin to look like this red line. Notice that when you apply airway pressure to the red line, you get less of a volume change compared to the blue line. It's because it is a non-compliant or stiff lung. And now let's talk about what would happen to the pressure-volume relationship of the entire respiratory system as a whole if we had a change in lung compliance. So here's the graph we looked at earlier. The green line shows the pressure-volume relationship of the respiratory system as a whole. And this point right here is the FRC, where the lungs come to rest after a quiet breath. If we had a change in lung compliance, the lung curve would look something like this. When we do this, it lowers the FRC, and that is a huge and high yield point for you to understand. Anytime we have a change in lung compliance, so we move from the blue line to the dashed blue line, our equilibrium point where the chest wall is balanced with the lungs is going to be at a lower value. So patients who have diseases where their lungs become stiff and become non-compliant will have a lower FRC. In contrast, patients who have diseases where their lungs become more compliant will have an increase in the FRC. So decreased lung compliance occurs in some of the disorders I've listed here: pneumonia, pulmonary edema, pulmonary fibrosis, and in all of these conditions there is a decrease in the FRC. Super high yield to know this for pulmonary physiology questions on step 1. At the bottom of the slide are some things associated with increased lung compliance. Patients who have emphysema have floppy lungs and the lung compliance goes up. As we age, the compliance of the lungs go up. And the presence of surfactant makes the compliance of the lungs go up. So babies with neonatal respiratory distress syndrome who are missing surfactant are going to have stiff lungs. So if you have these things present, if you have emphysema or you're older or you have lots of surfactant in your lungs, that's going to increase the compliance and that will raise the FRC. And the fact that emphysema is associated with increased FRC is what leads to the barrel chest. This is something that you can appreciate just by looking at patients who have emphysema. Emphysema causes the lung compliance to increase. As I showed you before, that raises the FRC, so these patients have more volumes of air in their chest at all times. As a result, over time, their chest begins to expand, so instead of looking normal like this guy, they have a barrel chest right here. Everything you see here is caused by an increase in lung compliance and an increase in the FRC, all tied in to those pressure-volume relationships we've gone through in the last few slides. Now let's talk about forced exhalation. When you use all your muscles to push air out of your lungs as hard and as quickly as possible, the physiology of this process of forced exhalation is different than the physiology we've been talking about for normal quiet breathing. During forced exhalation, the pleural pressure becomes positive. This is going to compress the airway and put pressure on the alveoli and generate positive pressure in the airway, much higher than what you get during normal quiet breathing. And this is going to push air out and air is going to flow from the airways. So let's take a look at this alveolus I've drawn on the screen here. What happens during a forced exhalation is that the pleural pressure becomes positive. So remember I told you before, during normal quiet breathing it's always negative, but you can make it positive if you try to push air out of your lungs as hard as possible. So let's imagine that we create a pressure of positive 20 in the pleural space. What that's going to do to the pressure in the alveolus is make it even higher than that. It's going to be about plus 35. The reason it's higher is because not only do you have the plus 20 of the pleural pressure, but remember the lungs want to collapse in on themselves. That's called elastic recoil. So that pressure is added additionally, and therefore you get a very high pressure in the alveolus, like plus 35. And remember that atmospheric pressure is 0, so now you have a very large gradient of 35 millimeters of mercury driving airflow out of the lungs, and that's why you're going to get a vigorous forced exhalation. So you might be wondering, if the pleural pressure becomes positive, why doesn't it collapse the lungs? So let's talk about that now. This involves an important pulmonary physiology concept called the equal pressure point. So let's look at this alveolus I've drawn at the bottom of the screen. We're engaging in a forced exhalation. The pleural pressure is positive at plus 20, and the alveolar pressure is even more positive at plus 35. And out here, the atmospheric pressure is 0. Now the pressure does not go from 35 to 0 all in one step. The pressure slowly drops as you get from deep within the lungs inside the alveoli all the way out to the atmosphere. So the pressure might drop, for example, to 25 at some point, and then at some point to 20. This point 20 is called the equal pressure point because now the pressure inside the lungs is equal to the pleural pressure. Once you go beyond the equal pressure point, the pressure inside the respiratory system is lower than the pleural pressure, and this is where the lungs would collapse, but that doesn't happen. And the reason for this is because in healthy people, this point beyond the equal pressure point occurs within the cartilaginous airway. So in the video on pulmonary anatomy, I talked about how some portions of the airway have cartilage and some do not. In healthy people, the equal pressure point occurs within the cartilaginous airways, and therefore the pleural pressure cannot cause collapse. So I've summarized these points on this slide. The equal pressure point is the point where pleural pressure equals the airway pressure. Beyond this point, the airway collapses, but in healthy lungs, the equal pressure point occurs in the cartilaginous airways, and therefore airway collapse does not happen. Here's a slide that I go through in detail in the video on pulmonary anatomy. It shows the respiratory tree all the way from the trachea through the bronchi and bronchioles all the way down to the alveolar sacs. And as shown on this slide, cartilage is only present in the early portions of the airway. There's cartilage present in the bronchi and in the trachea, but there is no cartilage in the bronchioles on down to the alveolar sacs. So in healthy lungs, the equal pressure point occurs somewhere above the bronchioles. It occurs somewhere in the bronchi. These bronchi have cartilage, and therefore they don't collapse even when the pleural pressure becomes higher than the airway pressure. If the equal pressure point were to occur here in the bronchioles where there is no cartilage, that would be bad, because without cartilage the airways can collapse if the pleural pressure becomes higher than the airway pressure. In patients with diseased lungs, however, the equal pressure point moves towards the alveoli, and therefore it can lead to airway compression. Let's look again at the bottom of the slide here. So let's imagine that we have a pressure of plus 20 again during forced exhalation. And now let's imagine that the equal pressure point has moved this way towards the alveolus. Now we reach a situation where we've got higher pleural pressure than airway pressure outside of the cartilaginous airways, and that's going to lead to airway collapse. This can happen in patients who have airway obstruction, like from bronchitis. We'll talk about that in a minute, but the pressure drops more rapidly there, so it goes from 35 to 0 more quickly, and therefore the equal pressure point occurs closer to the alveoli. This can also happen in emphysema because there's a lack of elastic recoil. So when this happens, when the equal pressure point moves towards the alveolus, it can be reached in the thin-walled bronchioles that don't have cartilage, and the result is airway collapse, obstruction to airflow, and air trapping, all of which are features of lung diseases like bronchitis and emphysema. So here's what happens in emphysema shown at the top of the screen. There's loss of elastic recoil. So when you generate that pleural pressure of plus 20, instead of getting plus 35 in the alveolus, you only get plus 25. That pressure is going to drop quickly and reach a value lower than the pleural pressure at some point before the cartilaginous airways. In bronchitis, what happens is there's more pressure drop compared to normal because of obstruction to airflow. So let's look at this example of plus 20 in the pleural space. We still have our elastic recoil intact, so we generate a pressure of plus 35 in the alveolus. But because the walls of the bronchioles and the bronchi are inflamed, there's more pressure drop as airflow moves out of the lungs. So instead of going to plus 20 and plus 15 at a point in the cartilaginous airways, we reach that point early, and therefore we have collapse of the lungs. And the key point here, and what they want you to know for your board exams, is that in these disorders, the equal pressure point moves towards the alveolus, and that's what causes it to be reached when you are outside of the cartilaginous airways. So patients with COPD have this problem of airway collapse when they breathe forcefully, and so they engage in certain behaviors to prevent airway collapse. The first thing they do is they slowly exhale. This prevents the pleural pressure from rising significantly, because if they breathe more vigorously, the pressure would rise and the airways would collapse. So by doing a gentle, slow exhale, those pleural pressures never get so high that they can collapse the lungs. The second thing they do is they purse their lips. Whenever you purse the lips, you create an obstruction to airflow, and pressure builds up behind that obstruction. So pursing the lips is going to increase the airway and the alveolar pressure, and this is also going to prevent collapse.